the whole world at our feet, watching seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand, open arms. This is home where we are, ever strong in the world that we made. I still hear you in the breeze, see your shadows in the trees, holding on, memories never change.
Okay, good evening everyone, and let's see if you can hear me. Okay, Obs says you can hear me, so you should be able to hear me. Good evening, and welcome to another of my live streams. Today's moderator is KrzaQ. You can see his nickname right here, so if you do have any questions during the live stream, just tell KrzaQ, and I will not see them because I again forgot to open the question panel. I apologize. Let me quickly do just that. Okay, now I will be able to see your questions. But again, you need to ping KrzaQ on, if you are on YouTube chat, Discord, IRC, you have to ping KrzaQ to actually, for the question to actually get to me. Yeah, that's how it goes. I don't look at the chats all the time, I sometimes do look. And today's topic is going to be basically reverse engineering VM-based reverse engineering protection, basically, which means there will be a program which was protected using VMs, and we'll have to figure out how to approach it, how to analyze it. And there will be, I will actually, I guess, do a 10-minute introduction to tell you what is this VM-based anti-reverse engineering pattern, and what is it good for, why is it not good? It sometimes is good, by the way. And what twists and plots you can do. And then I will do the reverse engineering. Now, the question might be like, will I be using IDA for the reverse engineering? Will I be using Jidra? Will I be using Binary Ninja? It actually doesn't matter. Not in this case. Not due to the sample which I've chosen, because we won't be using our disassembler a lot. We will be using it a little, but we won't be using it a lot. So yeah, it will be fun. And basically, like, VM reverse engineering is where you look at your tools, look at IDA, but you need to do a lot of your own tooling, and this is what we will be doing. We'll be basically creating our own disassembler and trying to figure out what's going on. So yeah, except we'll be writing our own IDA. Of course, that is way like over-exaggerating, but we will be writing a disassembler. Cool. So before we get that, let's go with... Oh wait, that's actually a good question. Did I check this? Yes, of course I forgot to switch my desktop to be on the proper monitor, and you would not see the proper desktop, and that would be quite embarrassing. But thankfully I did some clicks, and now you can see my desktop. And since you can see my desktop, we can go with some usual news, so folks can basically come and join our live stream before it begins. So our moderator again is KrzaQ today. This is his website. It would be dev KrzaQ.cc, and I decided not to ask where is the new blog post. Well, okay, I just did, but I decided not to do it because at least until I write something new on my blog. Because I guess if you go to my blog, yeah, then let's see. It has been a long time since I've written something technical. There was this challenge on the Polish part with some tickets to the Polish conference, and there is like, yeah, like basically an ad to my project, ad for another of my project, ad for our chat, winners of a competition. Yeah, I need to write something technical. So I will mock KrzaQ after I write something technical. Unless he does it first, then he can mock me, I guess. Yeah. Cool. Next thing. Since we're talking about my projects, Paged Out is going to be released, I guess, in July-ish, maybe late July, but we are still looking for articles. And speaking of articles, we actually published another example article that would be how to unboringly tease Google CTF 2019 by Reverse It. And Reverse It, you might notice his channel on YouTube, and you might really want to take a look at this article. I'm actually going to show it to you. It basically, the author takes a challenge from the last Google CTF, the beginner's track, and says why the challenge could have been improved and in what ways. And also actually improves the challenge. Like it is not written how he improved the challenge, but the task, like the challenge for you, for the readers, is actually included in the article, either in the form of the link in an easy version and not so easy version like this thing here. And so totally take a look at this. There might be some, like this might be also interesting to you. So do take a look. And yeah, I totally would recommend checking out the project itself. We are still missing 18 articles before we get to this boundary. And I know another article was submitted today, so that would mean we are missing 17 articles. And once we get to the 50, the boundary of 50, then we will start like finalizing the first issue of Paged Out, and it will be available for free to download once it's published. Now, if you want to write an article, like I totally recommend, do check this, like call for pages and writing articles, pages, and then write something. We welcome technical articles from like these topics, and we welcome them a lot. We are still missing several articles, especially like retro computing or demo scene. We have some for retro now, but we have nothing on demo scene, and we would greatly appreciate that. Cool. So yeah, and thank you to everyone who already submitted. Next one, speaking of Google CTF, the Google CTF qualification round 2019 is going to take place on the 22nd of June. That's Saturday, and it will go all through Saturday and Sunday, at least in my time zone. So yeah, do take a look. This is, by the way, a photo from the finals from London from last year. We can see like some top teams here, a Dragon Sector on the right. I'm not really sure who sits here on the left, but like it was really cool, and like the venue was quite amazing. And there might be some challenges from me as well. So if you play and yeah, you might stumble on some of my challenges as well, since I'm helping with a CTF. A lot of people from my team are helping with a CTF, so I really invite you to play. And there will be also the beginner's track. If you do not feel strong enough to compete in the qualification round, there will be multiple challenges for beginners in the beginner's track, like last year. And I'm pretty sure we're going to talk about them at some point after the CTF as well on one of the live streams. So I encourage you to mark the date. That would be in 2 weeks, actually. Yeah. And we get to, I guess, today's topic, which is going to be this task. It's called Just Another Matryoshka. Matryoshka are the, Russian dolls. You probably know, but just in case somebody doesn't know, these are like these dolls where there's a doll inside a doll inside a doll inside a doll. Like very famous. I'm pretty sure everyone knows. Yeah, so I'm just saying this without a reason. Anyway, and the description for this challenge was, I'm sorry, I'm so sorry. This is the description for the task. And yeah, And you can see like virtual machine already here, so that's a little bit a spoiler. I'm going to give you a link to download it if you would like to. Wait, that's the spoiler download. I don't want to give you the spoiler downloads. So wow, Facebook, that just doesn't work. How can I copy this link without it looking like crazy? Alright, I think I cannot, so let me just do this. Okay. And it works, perfect. So now now I can give you a link. I can follow the link. Yeah, but if I follow it, it will actually download the file. So, or can I click like, yeah, whatever. Well, it doesn't matter. And yeah, I'm going to take a look if there are any questions, and if not, we can jump right into the topic. Oh, there are actually 2 questions. So you will see the questions here. Again, if you have any questions during today's live stream, you have to ping KrzaQ, because he takes the question and he puts it in our panel where I can see it. I do look at the chats, but not so frequently. Do you like using touchpads in laptop? No. 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 Touchpads are basically like... no, I actually, in all honesty, I always have a mouse with me to connect to a laptop. I can use it. I've done multiple presentations, like slides with a touchpad and with whatever is the other thing, like a mini joystick called. And yeah, but I'm not a fan of touchpads. What manages the cooling in a PC? Is it a driver, an operating system, a BIOS, UEFI? That's a good question. I actually don't know, in all honesty. It can be any of these things. And it can also be some hardware which is somewhat programmable, like some piece of motherboard. I'm not sure. It's a good question, but I'm not sure which part exactly is managing it. And did I hear about RAM bleed? Yes, it's hard to open the fridge and not find RAM bleed there. It's basically, the idea is like you have Rowhammer, the old bit flipping attack, and now they're using like, I'm not sure actually what techniques they're using, but they are able to leak specific bits from the physical memory, and they actually leaked a private key. I didn't read the paper yet. I am going to read the paper because I'm really interested in this kind of stuff. So yeah, but I don't know how it works yet. But like in severity, I would say Rowhammer was actually more severe, because being able to flip the bits can grant you code execution easier than just being able to read the memory. And if you get code execution, you can just like plainly read the memory without using any tricks. That being said, it's still like sounds like a pretty interesting attack. If I read the paper, we can try to make a live stream about it if it would be interesting, and both about that and about Rowhammer. Cool. I'm not sure if you could actually see questions there. Oh well. So I guess we can go to today's topic, which again are like how to reverse engineer a virtual machine. Now, this is going to be our crack. We already downloaded the Matryoshka challenge, like just another Matryoshka. And what is it? It's a 32-bit ELF executable with Intel, and it has, it's not stripped, it has like debugging symbols. Perfect, that's easy. We have debugging symbols, that's also, well, that's actually like half of our job done, right? I hope so. What you usually do is you like do, not strip, you do strings on this just to see if there are any flags plainly visible. There are a lot of symbols. We're using, like for this CTF, we are using the D, R, G, and S for flags. No, we cannot grab to win. So it sometimes works, but, well, rarely works. Only if the challenge is really broken. It didn't this time. Now let's try to run it. And if we run it, it says like just another Matryoshka. It was from the Confidence CTF 2015. And it says password, please. Okay, password is ASDF. Verifying password, nope, sorry, wrong password. Okay, so now we know how it looks like. Now let's take a look at the code. What about, okay, that's a nice joke. What about this in the reverse? Like DRGNS in reverse, the iPhone 5 asks. It's a good tip, by the way. No luck there. I guess we could like look for a brace. And there are some braces there. Wow, this is, I don't know what this is, but this looks like C++ errors. But no, nothing that looks like a flag. So now I'm going to open it in IDA. I guess in IDA, I mean, you can open it in anything which you like. I'm probably going to switch to GDRA at some point, but for now, since I have it installed. Okay, and it's loading. And I'm going to use a decompiler because it doesn't really give me anything for this challenge. And GDRA has a decompiler as well, so come on, come on. Okay, here we go. So it outputs the ASCII art. Then it says password please. It uses scanf to read up to 32 characters of password, and that's 32 characters plus a null byte. So we know that the password is up to 32 characters. Then it says verifying passwords, and it verify password, and then result is equal to 0. Otherwise, if you do not put anything, it says like yeah, and it says result is either 0, which is pretty weird, but okay. So yeah, it calls this function, and it doesn't even pass this password because the password is global. I guess you can see by the color in IDA. It's like if something is blue, that means it's a global. So it's a global variable. It's actually here at this address. There is a. It says the buffer is like 1000, but that's not really 1000. It's 400 hexadecimal, which is like 1024 in decimal, but that's not the case. So if we go back here, let's look at the verify password. And this is the function which we have to analyze, which is verifying the password. So this is the function which we'll be focusing on today. Okay, I do not see anything here. Let's take a look at assembly code in that case. And, oh well, we push EBP, we swap EBP with ESP, and then we move this address to ESP and return to it. And that's it, that's the whole function. So what's happening here, if you've ever done exploitation challenges, you know what's going on here, and this looks like basically, well, okay, if you even done reverse engineering, this is a pretty simple way to do a jump, right? Well, not really. This is a pretty simple way to do a stack pivot and then do a jump. Because this is actually what's called a stack pivot, which means we have, you know, like, you have the memory, and then you have like, your stack is normally here, but you have some controlled data here. So what you want to do is you want to switch the stack pointer to the area where you control the data, and this is what's going on here. It's actually doing a stack pivot to some other area. And then it does return, which basically means it grabs from this new area, it grabs some return address, and it jumps there. So I guess it looks like return-oriented programming, which we are going to have to look at. Now, before we get to analyzing the return-oriented programming, you have to know that return-oriented programming is basically a virtual machine. And it's basically a really, it's called like a weird machine implementation of a virtual machine. So each address where we return to a separate gadget, that can be thought of as an opcode. Like a gadget is an opcode, basically, an opcode of a virtual machine. So we'll have to reverse engineer the gadgets to see what's actually going on in that code. Now, before we get there, I promised you some, like, you know, theory, like why do you use virtual machines in anti-reverse engineering? So let's get that out of the way so we can focus on that. Now, it's basically like this. The reason for using anti-reverse engineering techniques is to slow down the reverse engineer who might want to look at your application, right? It can be thought of like you have some really secret algorithm hidden there. You might have, for example, some DRM hidden there, for example, like checking the product key, or you might be a malware author and you want to slow down the analyst who is actually looking through the code of of your malware, right? So there are like, again, reverse engineering is just a tool, and anti-reverse engineering is just a tool, and is used by multiple parties for different purposes. So regardless of this, well, there are multiple ways to do anti-reverse engineering. For example, you can fight with the debugger, right? You can try to detect the debugger, try to kill the debugger, try to complain if you detect a debugger, try to like sidetrack execution to a different path if you detect a debugger to like make things complicated, and basically like honeypot the reverse engineer. So that's one way. The other way is to make the analysis itself more painful, because reverse engineering is all about being painful, about being long. It takes a long time to reverse, especially an obfuscated application. So yeah, people do like obfuscations in different ways. You can, for example, put a lot of garbage instructions in between, so every like 10 instruction you read is only valuable. So yeah, like you just lost time to read all the other 10, and you have like hundreds of instructions multiplied by 10, and so that's not pleasant. Another approach is like to do spaghetti calls, as in you insert, like you spread your code all around the memory and you do jumps from one place to another, to another, to another, to another, to another. The processor, the CPU doesn't care about jumping, but when you look at it in IDA, you're like, this is going to be painful. By the way, you do tracing in that case, instead of doing like a normal static analysis. And another idea is basically to implement a virtual machine, as in the algorithm which you want to protect, you like write it, I don't know, in C, it doesn't matter, you write it in some form of a programming language, and then you compile it or assemble it into a custom bytecode, a bytecode which you invented and which you implement in the virtual machine. So that way, if somebody looks at the, like in IDA, they compiles the code, they see the code of the virtual machine, but they do not know what the virtual machine, what code on the virtual machine is executed. Well, they can disassemble it with what? You created it. You created the virtual machine, so there is no tooling for it. And this is where basically like the, you know, the more junior reverse engineers say like, yeah, maybe I'm going to do a different thing. But this is a good thing to actually like do it at least once. It's easier than it looks. What you have to do is you have to analyze the virtual machine, pinpoint all the all the opcodes, like, and also pinpoint how the bytecode is constructed. There is only a couple of ways to do it, and almost everyone is using the same techniques. And once you have it, you have a list of instructions, basically a list of opcodes, and you know how the opcodes are formatted, you can write a disassembler. Once you can write a disassembler, you can, well, disassemble the bytecode, which is somewhere else in memory. It has to be there. Because again, reverse engineering and like computers are not magic. If you want to execute something, it has to be somewhere in the memory. So you take the bytecode and you put it through your tooling, which you've written, and you get an output, and you analyze the output the same way which you, like how you would normally analyze something, without the compiler maybe, but like, you know, reverse engineering is all about assembly anyway, well, almost. It's also about Perl, which you've written 2 weeks ago and you cannot read. So yeah, so that's basically it. Now there are a couple of twists and improvements you can do on the virtual machines. For example, you can implement a generator for the virtual machine, as in you can actually you know, the bytecode, you can select the opcodes, but you can also like randomly select the opcodes each time you compile the bytecode. And so you basically like, you have your program, your algorithm, which you want to make really hard to understand, and then you basically like have a generator which takes it, generates a random bytecode, and generates a virtual machine for that random bytecode. It's not hard, it's actually rather easy, even though like this generating might sound scary. It's not, it's super easy to do. And that way, even if somebody creates a disassembler for like this product, then it will not work on another product using the same technique, because surprise, surprise, the bytecode got like shuffled and like the opcodes don't match and your disassembler stops working. You can actually do even more fun stuff. For example, you can, after each jump in the virtual machine, you can randomize the bytecode, like in a pseudo-random way. We also created with you a crack me like that several years ago. It was quite fun. So that's one way you can improve it, and the other way you can... oh, by the way, that's also defeatable. You just need to know it's a generator and how to analyze automatically the virtual machine. You can write tooling for that. I've done that in like at the beginning of my career when I worked for an antivirus company. So you can write like automatic disassemblers and analyzers even if a VM is generated randomly. And another thing which you can do is you can basically write stacked VMs. You can implement a virtual machine and then in the bytecode implement another virtual machine, which executes another bytecode in another virtual machine, and so on and so on. And you can have like 50 or like 100 layers of a virtual machine. It bloats the code a lot, of course, but it makes the analysis really, really painful. So that's a really decent technique if you want to slow somebody down, because they have to figure out how to like automatically, you do not want to do it by hand, how to automatically disassemble one VM after the other and analyze them without doing it by hand. It will take a couple of weeks to basically get through this. So that's the theory. Now let's get to business. Let's get down to business. But how to get to business if we do not see what business is? Well, as I said, this is basically a stack pivot, which means that under this address we will find our stack. So let's go there, and what we can see here, there's some marker here, it's called alt stack. I guess alt stack would be for not alt stack. It's alt as an alternative probably, or alternate stack basically. Well, alternative, I guess, main English, yeah, whatever. This is some marker, but it doesn't really matter. I guess how is it in x86? If you push something on the stack, the ESP always like points to the next item on the stack, not on the last pushed, right? So the ret would actually grab this thing, these 4 bytes, and it would be great for us to like reformat this in this way. And this should be an address of some instruction doing something. So if we jump to it, yeah, it is some code doing something, which is cool. Now, what we want to do basically is we want to figure out how long is this, like how many opcodes do we actually have here. I guess we can like take a look, but yeah, there's a lot of it. So we probably do not want to, yeah, I do not want to scroll down. What I want to do now is I want to start writing my tooling for it. And what my tooling is going to do, okay, where is the beginning? What my tooling is, oh yeah, here it is. What my tooling is going to do is my tooling is going to basically, I will start writing a disassembler, basically, that's what I'm trying to say. So let's call it dis1, as in the first disassembler. And it's going to be in Python 2, as usual. I don't think I'm going to need to do anything. I'm going to need to open the, oh, you know what I'm going to need? I'm going to need from struct import everything. And now I need to open this file, which is called just another Matryoshka. And I need it as this, and I need to read it into I don't know, a byte array. Let's say I didn't care too much. What I care about, however, is some helper functions. So let me copy the helper functions from my pawn base, my, you know, the usual stuff I use for the CTFs. If you see me on the live stream writing an exploit, I'm using this. And these are just like super easy functions, which are wrappers for unpacking a byte, unpacking a word, unpacking a double word, and unpacking a quadruple word. And also the same for packing. So there's no magic here. I'm not going to talk about that. Yeah. And now that I have this, I can basically read the file somewhere. Let's read it to, I want to read it to a byte array. Let's read it to a byte array. But I didn't, well, whatever, that doesn't matter. Let's call it data, or just D. And let's read it. Okay, so now it's read. And now what I need to do is I need to basically read all the... Why does it even need a marker? I'm curious what this marker is for. Is it just there for fun? Maybe I had some scripts which are relying on it when it was building a KrzaQ. I don't know. Cool. While I is less than length of d, I is of course this, then okay, there's actually a function called for, which I can use here, and x range len from 0 to len d, step 4. Perfect. And now what I want to do is I want to have like d words, like a bunch of d words, which are going to be a list, and I want to put all the d words there. So I'm going to grab all the packages of 4 bytes and then change them from the 4 bytes into a d word, little endian d word of course, and I'm going to put them in that array. So to do that, oh sorry about that, to do that what I need to do is I need to do d words append and read a d word from the value, which the value will be taken from d. I need 4 bytes, and that's it. And now I can like for a d word in like I'm going to call it data after all. So here's okay. For d and data, for d words, print hexadecimal representation, actually like hexadecimal padded with zeros of the d word. And I guess I also could use an address of some kind, so let's do enumerate. This way I will know how many. Do I want a hexadecimal counter or a decimal counter? Let's go with a hexadecimal counter. That's usually better, but I do not think there will be a lot of them, so I'm going to go with this. And I'm going to multiply it by 4 actually. I'm wondering also if I don't want to add the beginning, like this address there. Maybe I am going to do that. So I am going to multiply it, but I'm also going to add the address there. And apart from adding the address, I'm going to do one more thing. I'm going to actually get I here as well. So here, if I added the address, I need this, but I also need just the counter, so I know how many instructions there are. Okay, yeah. Now we can run it. Where is my console? Here we go. Yeah. I found this and something broke because I did printf. Unpack requires an argument length of 4. Oh, this is... Wait, this is fine. Why are you complaining? Sorry, I forgot the important things. I give it an offset of where this is placed. This is at 820808 to 080, and it ends at... Where does it end actually? I'm going to go from the end, so I'm going to go to BBS, and this is probably it. No, this is not it. This is a really large section, but there are a lot of zeros here. Maybe it's not as long as I thought it is. Okay. There's probably a smart way to do it, and I'm not using it right now. I'm going to go with page up. Okay. I'm going to assume it ends at this address, because why not? So this address is actually A3200. A3200. Okay. Yep. Perfect. So now there's a question of... It's like this. This is ROP, like this is standard return-oriented programming, which means every return address, which means we'll have like addresses of pieces of code, right? This is, if you even don't understand return-oriented programming or ROP, what you need to know is that it's basically jumping between pieces of code, where each piece of code is like, ends with a return address. It's basically like a list of functions to call, or a list of pieces of code to call, which means that all the addresses which are containing code will actually have to be in the executable section here, right? So where do we have the executable sections? These sections. Well, probably actually, if we care about alignment, it's... No, this is DB. Yeah, I would say like around here we would finish. This stuff here, is it still executable? Yeah. It's executable, this is executable, and the beginning here is executable. So we go to raw data, we go to end of this page, and the end of this page is no longer executable because the beginning of this section, the first page of raw data, is still being executable because you cannot apply different attributes to the same page. And the page is 4 kilobytes, right? A page 4 kilobytes, and this address isn't aligned for raw data to 4 kilobytes, which means this is executable code. And it ends with FFF, the end of a page. So the end of a page is going to be well, we don't need to scroll, we know it's just FFF, right? So exec code is basically between, this is the end address, and I'm going to make this FFF, and the beginning address is the beginning of the executable space. And an important thing to note here, usually folks go just like, oh, the executable code, that's in text, but you have to be aware that executable code is everywhere in the section of memory which is executable, which means like also this PLT, this load, this init, whatever. Everything which has the executable attribute runtime. We are not looking runtime, but runtime is executable code, which means just to be safe, just to be sure that the author of this challenge, of this VM, didn't do something funny with placing code in non-text section, we want to cover all the executable sections. That's why I'm not only focusing on text, I'm focusing on everything which can be executable. It's also a good habit to have if you're looking for gadgets, because sometimes you find gadgets like in PLT or init or whatever just by accident. So keep that in mind. Now this is the beginning address, and this is actually the beginning of the binary as well. So yeah, I'm going to take a quick look. Okay, and now, yeah, now what I can do, thanks to this, is basically automatically mark which pieces, which keywords here may potentially be references to code, which means might be actually things which get executed. Once we have that, we can calculate how many unique addresses are there. Because it's not going to be, everyone is not going to be unique. We will be jumping all the time between the same gadgets. So we want to take a look how many gadgets are actually used. And once we have that, we have a nice list of gadgets. We can start and describing the gadgets, basically. And everything else is going to probably be either a pointer to something, or it's going to be, which is also interesting, or it's going to be just an argument. And we will look at pointers in a second as well. So pointers are actually let's call it executable code, let's call it data reference. It's going to be any address which is not executable. Did I just break something? Whatever. Which is not executable, but it's still in this binary, which means basically from the raw data section up to the end. Which would be this like thing here. So I'm going to transcribe that thing here. So the end is going to be 81ED824, and this is the end address, by the way. The beginning address is basically going to be this +1. So +1, that would be wait, let me make +1 is just C. Oh, okay. This isn't super precise, but it's good enough. We might have like data references somewhere in this executable code as well, but if we get to that, we will deal with it on a case-by-case basis. And here I'm also going to do FFF. Yeah. That's fine. Now, let's do something like this now. I'm going to create a set of gadgets. Gadgets. How do you spell gadget? Gadget? Yeah, like this. I'm sorry, this went like blank for a second. Okay, so this is going to be a set, and if the given D word is in between executable code, so executable code of 0 is less or equal to D, which is less or equal to executable code of 1, then this is like Python is the only language I know which supports this kind of expression. Usually you have to split it to something less and something less. But again, if it works, it works. Then we actually add it to the gadget set. We add this. Okay. And we know also it's a gadget. So like let's put something like create an additional description. And in this case, the description would be it's an like unknown gadget. Yeah. Else if it's actually in the data ref zone, so 0 the data ref, then we add to not to the gadget list, we just save at the desk as like a data ref. So data ref, is it a data reference? And here we are actually going to do 2 spaces and then the description. Perfect. Now we can run it again. Wait, before we run it, I want actually to print out the gadgets. Print out gadget. Gadgets. Yeah. Perfect. So yeah, as you can see, we do not have too many gadgets. How many gadgets do we have? Print len gadgets. I'm not going to count it. We have 15 gadgets. So this is all. This is our, and again, treat each gadget in this case as a separate opcode, separate instruction in some weird assembly language. So we have 15 assembly instructions, not x86 assembly, this weird assembly. Yeah, and we have like using them a lot, and there are some data references as well, some addresses which look pretty sane. Actually, we can take a look what's there. So let's go there. There are some zeros, maybe it's like global memory used by this virtual machine or whatever it is. And there are also some weird things which I don't know what they are, but they are here as well. And how many instructions do we have total? We have like the program is 450F, and that's hexadecimal. That means like 1070. No, wait, 1100 something. D words, but the number of actual unknown gadgets here is less, not a lot less, but it's still going to be a pretty long program, I would say. Cool. Now what we have to do is we basically have to print the gadgets and go one by one and analyze them and create some form of a description of it. So like, let's call it opcodes. And we're going to have a set of opcodes, and we're going to grab this, but we want to print it as like hexadecimal. So print. How do I even do that? Oh, I can change it to a list. Gadgets, is it fine? It's fine, okay. So, for G and gadgets print hex G. Okay, thank you very much. And these are all the gadgets which we need to analyze. I'm going to put them here in the opcodes. This is exactly what I didn't want to do. This and this is going to, we're going to probably create a function for each of them to disassemble it for like, oh, let's do it like this. I'm going to put like 2 things here. Let's put none here for now and the description of it here. And yeah, okay. And then what I'm going to do after the analysis here, I'm going to actually say if the D is in, the D word is in opcodes, then the opcodes of D is not empty. This is enough to say not empty. Then the description is actually going to be this. So this way we what? Oh, right, commas. Okay, so commas, perfect. It's really nice that Python actually allows the comma next to like the end of a list or whatever. Yeah, so if we run it, well, it basically shows this like, oh wait, that's totally wrong. Zero. Yeah. Okay. And now we have to start to disassemble. Let's go one by one. So let's go here and let's analyze this. What do we have here? This is basically, you can zoom it, right? This is a so-called peek instruction. Peek as in peeking in memory. So in EAX we have some address, we add 4 to this address, and then the from that address +4, we basically take 4 bytes and we put them in the EAX register and then we return. So this is, again, this is a peek instruction, and I do believe we are jumping. What we need to always double check is whether we are jumping to the beginning of the instruction or are we jumping to the middle of the instruction. Because if we look at the hex editor, it marked 3 bytes. What if we actually jumped here? I know it still shows the cursor on the same line, but it doesn't mean the interpretation it shows is correct in our context. So we have to be mindful of that. And I'm probably going to fail that today, at least one. Okay, so yeah, again, this is a peek instruction for me. I'm going to just note it basically for now. This is like peek, and to EAX we put EAX +4. Okay, so now if we run it, we can see that it's like sometimes already showed in the description. However, in the description, what we want is also 0. Yeah, better. Yeah, perfect. Now, what we are basically writing here is our disassembly of it. There will be some opcodes which will have parameters and we will have to deal with them later, but for now let's just go with the easy ones. Here, where do we jump? We jump at the beginning. This is IO puts, alternative name. This is puts, this is just a function call. So this is puts, or like call puts, whatever you want to call it. So we have some call puts. Oh yeah, we have like a call puts there, which means it's probably like shows some text. So yeah, let's go like with one by one. We'll analyze whatever is going on there later. Here we jump into 22, which is exactly this instruction. This is a poke instruction. Poke instruction, and again, we are only looking at like this because we are jumping to this code. A poke instruction is where you take 4 bytes and you put them in memory. You poke them in memory. And yeah, so we note it down. This is a poke. The peek poke naming is, by the way, from Atari Basic, from all the basics. And I'm using peek poke because I used to start learning programming on Atari, and I just know peek and poke by heart. Basically, you can put it you can call it like store and load, for example. Like peek would be, in this case, would be a load, and poke would be a store. Let's maybe use this because I'm pretty sure people are more like know this actually better, like the store and load instead of just like peek and poke. And this is putting ECX in. So let's use the in the Intel convention, and we put here the value of ECX. Okay, perfect. And now once we have this, we can take a look at the next opcode, which would be here. So let's jump here. And we are not, yeah, this is the first case, E4, this is E4, right? But as you can see, the instruction is actually E3. So what we need to do, we need to decompile it, undefine, and we need to go to E4 and we need to, we need to like undefine it. No. And now we need to disassemble it from here, so I'm pressing C. And ooh, it changed to a different interpretation because we started disassembling from the middle. That's how assembler works. Like, yeah, if you jump into the middle of the instruction, it's a different instruction. This is basically like an exchange between, this is a stack pivot. Yeah, so this is a stack pivot. I'm going to mark this as a stack pivot. So this is a stack. You know what? I'm going to use lowercase. Load store stack pivot, and I'm going to like mark it like swap EAX ESP. It swaps the value, exchange swaps the value of these two registers. So if something was in ESP, it's going to be in EAX and the other way around. Cool. Now we go to this. What do we have here? Is the address correct? No, it's not correct again. We have to undefine it. I'm pressing U and enter. We have to go to 6. 6 is here. And this is a pop EAX. This is a set EAX. So this is like pop EAX or like set EAX to whatever is on the stack. This is also the first function which I'm actually going to do something different. I'm going to show you why. Let's find a pop EAX somewhere. Oh yeah, here we have pop EAX. So here, right? It actually, what it will do, it will grab this value, like this value, and put it in EAX. So instead of writing pop EAX, what we can do, we can write move EAX and the value, like O80ECOA4, because we are starting to understand how well we know, because this is Rob, so we kind of know the format of the byte code of this weird machine, and we can easily just disassemble it like this. So, but to do that, what we need a function basically. And so I'm going to use a function which is going to be called like opEAX, because maybe opcode. Yeah, and what the function is going to do is going to take 2 parameters, basically, well, 3 parameters. First is going to be this, and this is going to be, yeah, a format string, let's say. And so this is like a format. Then it's going to take the, basically and is going to take the D words as the, like, so D words and and is going to return how many D words it actually consumed. So in this case, we are going to grab like the parameter, the argument is going to be just 1 D word, so I'm going to grab it. Oh, let's maybe do it like this. I'm going to return I. That's a little bit easier. And now having this argument, what I want to do is maybe I want to return it. So let's return actually 2 things. Let's return the new I, and let's return the format with the... Sometimes we might want to ignore the format, but in this case, we want the format and we want the argument. Okay, perfect. And I'm going to change this to set EAX to this value. We can use set, we can use move. But just don't confuse it with x86 move. And now, what we need to do is we need to go back here. And here, we have to change it a little. If this is not known, if this is known, by the way, then we can do just this. Otherwise, if it's not known, we want to call that function. So wait, we're going to get 2 things here. The let's call it a new I, and we also get the description, obviously. So we call the D from 1, which is the function, with the arguments which I did mention, which is the format. The format being opcodes from D from 0, and then the current I, first the D words, and then the current I. Now, because I'm actually going to do this new I thing, I need to change this. So I need to do this. I need to do while I is less than the length of D words. And next, what I need to do is I need to set D to D words of I. Yeah, and now now it's equivalent. Apart from it's not increasing I, which is the obvious mistake I always make. And here, what we want to do is we want to actually I plus 1 put here, because first is our opcode and then the arguments. So this is I plus 1. And here what we are going to do we are going to do this. And this is the new I, which is fine, and we can do continue. Otherwise, if we don't continue, what we want to do, we cannot do continue. No, we just do this. And we already increased I1, which is pretty annoying. Now, you know what? I'm going to change it. I'm not going to do that. I'm going to calculate how many opcodes are actually used. So use 0, and here used +1. And we used 1 argument. This is what I'm going to return. So since we used 1 argument, we can do this. And that way, when we reach here, we can do I plus equals 1. Okay, this is now good, because otherwise it would complicate the logic. And it says new I not defined because it's used now. Yeah, and it works. Now let's look at our set move EAX. as you can see, it actually like consumed the next argument, which would normally be var. Actually, we can, if we comment this out, we will see that, where is the move? Yeah. We will see that it actually took this argument and it put it here. So we already have it like directly in our code. One thing I'm going to change is in this format, I'm going to go with OX. But we want to skip it. We don't want to show the argument anymore here, so we do this. Okay, perfect. Now we have already several gadgets analyzed. We can go and we have this infrastructure for actually parsing the arguments. And this isn't like the best way to create a disassembler. This is a fast way to create a disassembler. We do not care to make a perfect disassembler, unless we do, but not this case. In this case, we want a disassembler, which is custom, which can show us information which we can analyze to look at the task. Which means that now we have to go into IDA and jump to the next address, which is 28. Again, it shows 27 here, which means we have to undefine it. We have to go to address. We can jump just again to 28. We are at 28. I'm pressing C now, and it's pop ECX ret n, which is basically pretty close to what we have here, except that it's actually ECX. And I'm actually going to change this to opcode pop. Because we have a format string here, it doesn't really matter if it's EAX, if it's ECX, it's going to properly decode it anyway. So yeah, it's probably decodes ECX now. So the next thing we need to go is to go to here. Here is A, it's actually correct. And this is like pop EDX ret n, which is the same thing, but it's setting EDX. So I'm just going to tweak it here, EDX. And I decided this is annoying me, so I'm going to do a comma instead. I could do a equals as well. We can do it. Let's go with an equal. Yeah. This is now the compiler officially, since this is like a high-level syntax. Well, not really. Perfect. Now, next one. We go here. We check C, yes. Oh, and this is getting funny. This is a conditional move, which means if the 0 flag is set, this instruction is just a normal move, otherwise it's a no-op. So Z flag set, if it's set, then EAX is going to like take the value of EDX, otherwise it's a no-op, like do nothing. So this is getting interesting. It's basically like if 0 flag, then EAX has to be equal to EDX. Otherwise it's a no-op, nothing is going to happen. This means it's already a pretty advanced ROP, because you do not see this in non-advanced return-oriented programming exploits. ED, and this is another poke. Yeah, this is another poke. Address and EDX. So this is store EDX, but we actually put stuff from EAX there. As you can see, we have almost all of the virtual machine analyzed. So let's go next. Here, this is like, yeah, just transfer the value from ESI into EAX. So EAX takes the value of ESI. Next one. Here, do we have the address correct? 848, correct. And this is just a subtraction. So EAX is minus equal to E, or actually that's not minus equal, that's minus assign to ECX. Perfect. Next one, we are 4 to go, and the address is incorrect. So undefine, go to 2, and this is crazy. Okay, I don't know. This is crazy. This is basically a return. It grabs an address, it returns, and then it increases ESP by this value. So that's pretty weird. This is weird. I'm not sure in what context it's going to be used, but we're going to have to find out. ESI equals EAX, ESI equals EAX. Well, not equals. Assign EAX to ESI, obviously. Then address is correct. This is, if you could show it to me, whatever. These are these two instructions. Rep return does nothing, like this return, this rep, you can ignore it. It was, there was the story with this rep here is basically that I think in some, either Intel, but I think it was AMD processors, like AMD CPUs, if you had a return value in some cases, it would do something bad with the cache, but if you prefixed it with the rep prefix, then suddenly that problem, the performance problem was gone. So some compilers generated code with this return. But this might be also an accident, why I'm not sure why this is here, but whatever, I don't care. So this looks like a store where we store into the combined addresses of EAX and EDX, well, actually EAX plus EDX, and we put here a byte, and the byte is CL. The byte is taken from CL, and we have only one last byte code to take, 36, and we are at line 36, this is correct, and this is going to be, we do a load into EAX from EAX, so that's a peak, and then we add 8 to ESP, and then we pop EBX. Now this is funny. So what I'm actually going to do here is EBX equals to a value, and I need to like write opcode load pop, a new variation of this function to basically decode the proper argument. This is pretty weird, but okay. Okay, so first we skip 2 arguments on the stack, add ESP8, okay, add ESP8, so used is equals to 2, then we grab I plus 2, which is the argument, and we increase used by 1. This actually should be used like this, oh yeah, now it's fine. Because we pop EBX and we then show it, okay, and that's it. Now let's show how it, wait, not defined, my mistake. Okay, perfect. Yeah, now it looks a little better. I'm not saying it looks good, but it looks a little better. So at least we can like dump it somewhere. We do not have to do this anymore. And we can dump it to like this one.txt. This is the first version. We are going to do some magic to make our analysis and our life a little easier. But for now, we can take a look already at something. I'm going to quickly take a look if there are any questions. Yeah, there are some questions. So let me open this. And before we jump into the analysis of this, I'm going to take a look at some questions. So the questions are going to appear there, like on the middle of the screen. Do they appear? They don't appear. Something is broken. I don't know what is broken, but something is broken with our API to the server. That's weird. Anyway, the supervisor writes, did you use the NetWhite assembler trick for that or a C compiler? Here I'm pretty sure I didn't use either of the techniques for this layer of virtual machine. I did use partly for this task NetWhite assembler trick. The trick is basically to use macros in NetWhite assembler. I think that's the trick, at least the supervisor is referring to. So I didn't write a C compiler for this, or a transpiler, or whatever you want to call it. Khalid writes, can you give more details about how to randomize the instruction after each jump using pseudocode random generator? Okay, so it's basically like this. It's like key shuffling mechanism in crypto. Basically, the idea is that you have something which looks like randomization, but actually is a complicated mathematical function with predictable results. And if the results are predictable, that means you know after jumping what variant of bytecode you will encounter. So that means that you will piece the code together you have like piece of a code with like bytecodes being like sorry, no, let's go with this. Like you have, for example, like opcode A and B, which like A might be, I don't know, like move AAX1, whatever AAX is in this content, and this would be like red, for example, and then you randomize it and you might have like F would be this, and K would be red, and then after a jump, Z would be this, and like O would be red. So basically the idea is that when you write code, you can like write the code just like this. Your compiler can deterministically know which variant you will encounter after jumping, and therefore it can generate the code properly. So again, it looks random, but it's actually, and it might even use pseudo-random number generators, but it's actually fully predictable, and you need to be fully able to predict which variant of bytecode to generate for when compiling the target, right? And the virtual machine needs also switch to the same variant of instructions before going there. So you have the same instructions, like this instruction would be all the same, they just have different opcodes, which are shuffled around in a predictable way. Yeah, so I said it's random, but it's like not fully random. It's a little tricky to write, but if you get it correct, if you, for example, make the selection of the variant based on the address where you jump, that makes it really, really easy to do. So it might sound complicated, but in the end, it's a bunch of tricks which make it not really random, make it just looking complicated and deterministical, and it's quite easy to write. I fully encourage you to try to write it because it's pretty fun. And it's annoying to analyze. Not super annoying, but annoying. Source code deleted writes, if I understand correctly, are there any places that one might get ROP execution other than the text section? Yeah, basically anything which is in the executable memory, anything which has an X here, is fair game for your ROP gadgets. And yeah, that's basically what I said before and what I reiterated now. That doesn't mean, there will be vulnerabilities there or anything like that, right? But if you need gadgets, look in other sections than text. Matthias writes, question, how much will the performance differ from the original binary? They will, but actually depends on how much code do you actually compile into the virtual machine and run under the virtual machine. I did say for a reason that you only take the algorithm which you really want to hide and run that on the virtual machine, because there will be a dip in performance. Here, for example, due to this being a weird machine, a ROP-based weird machine, the performance don't really suffer a lot, but it's really easy to analyze as well, as you can see. So one virtual machine isn't so bad for modern computers. If you use stacked virtual machines, you only want to secure one thing, probably like the main important algorithm, and only parts of that. Are you going to BruCon? It's in October. Probably no. Where is BruCon, by the way? BruCon is in Belgium. Is it in Brussels? Probably, but not this year. I haven't been to Belgium yet. How do you say? Is it Belgia? It's Belgia in Polish, like Belgia. Belgium. Okay, I'm sorry. I told you my English is horrible today. Did you read about sponge-based control flow protection? How would you attack encrypted stream of instructions? I didn't read about it, so I'm going to note it. Thank you, who cares for the question, but I didn't read about it, so I might be familiar with the concept. I just don't know it by this name. Sorry. Okay, end of questions. So with that, we can get back to our show. It's not far from Swiss. Yeah, it's not far from Swiss, like Brussels. I mean, in Europe everything is pretty close, especially if you're from States or like from India, then that's not really true, but Europe is small. Cool. So now we need to figure out what to do here with this. And there is... Wait, what's going on here? Why? This is repeating a lot of times, and if something is repeating, that's really cool. This is initializing memory, because as you can see, there's a lot of this, like put into EAX some address, put into ECX whatever, and store it. Another address, and the address increases by 4, do notice this, and put another thing in ECX and store it, and so on. Address increases by 4 and store it. So this is storing, like initializing the memory. So let's go. There's a lot of this, and this is good because, like, I'm just scrolling, but we already analyzed this, and we do not need to analyze this further. Which means the actual thing which we need to analyze is shorter, and we like it. We like it that it's shorter. Perfect. Okay, so then we load something to EAX, we load something to EAX again, we set EBX to 0. This is not telling me anything. This is like there's some... what you usually do when you reverse engineer is you do not analyze each instruction one by one and think what it does initially. You do that as a last resort. First, what you need to do is you need to find like some things which look out of ordinary. Like, for example, this looked out of ordinary to me, so I noticed what it's going to do. Here, what I notice out of ordinary is this. This is like one if, another if, and there are a lot of stack pivots, as you can see. So it's a if and a stack pivot. A stack pivot in the context of a return-oriented programming is a jump. So the stack pivot is actually a jump. This says if ZF is equal to something, then actually jump to whatever is in EAX, and in EAX is EDX, which means that this probably is an address of this instruction. No, it's not. It's the address of what? Oh, this is EBX. I wanted to see this. This is the address of, yeah. So this means, like, this all means if the ZF flag is set, then jump to this address inside of a virtual machine. Stack change again is like ESP in ROP is your instruction pointer. Just to be clear, this is your instruction pointer. So assigning anything to it is jumping. So we jump there if the 0 flag is set. If it's not set, we jump here. And this, surprise, surprise, is actually the next instruction. It's like says 4 here, right? It's 4. And the next instruction here is actually, oh, I show it. It's on the address 8. But that's fine, because when red for first increases by 4, whatever is there, so it actually goes into this instruction. Like this address is, you have to increase it by 4. Yeah, perfect. And it continues. So, and as you can see, there is quite a lot of the same thing repeating. Again, repeating. What is actually being compared? We are using this for comparison. And it's just a subtraction, right? But subtraction in x86 also sets the flags, which is pretty normal. And if you subtract two numbers which are equal, you get 0. If you subtract any two numbers which are not equal, it won't be 0. So 0 flag is going to be set only if EAX, which is taken from ESI, is set to this value, or this value previously, or this value next. It's a switch case. This, what we are looking at, is a switch case. It's a series of ifs comparing always ESI to different values. It's a switch case. We are looking at the switch case. So we have the switch case, which all the time we jump to a different thing. And then we have, my bet is that the next thing we are going to have is actually where is it jumping to? But we have some storage things here. It's again some initialization of memory or whatever. And then we do this red, which is pretty weird. No, but it's not a return address. This is a string because it's puts, right? So it's a parameter for is it a parameter for puts? It's probably no. No, wait. The parameter for puts should be here. That's weird. Let's check it out. In IDA, what's there? Yeah, this is weird. I'm not really sure what's going on here. My bet is that we are jumping to this puts from 2 different locations and this is just garbage. I'm thinking if it can be anything else, but it's probably just garbage. On the other hand, it can jump like really, really low. Let's go, and we might have only part of our implementation. You know what we should do? We should actually take a look at where is this jumping. Is it jumping to some weird addresses which we don't have here? Yeah, this is not the complete virtual machine. I'm sorry. Which means let's find some address like this and let's go here. Yeah, this is where the virtual machine still continues. I was so happy that we are finally like close to solution, but it's not it. We didn't have the full machine. Okay. Okay, what we want is we want to go to the end of this, and to get to the end we want view, open subview names, and we want the sort by address, and here we want to find alt stack. So alt stack is here, and this is the end. Yeah, it's pretty long actually. Yeah, so this is where the alt stack ends, and there's some magical marker here as well. Okay, so this kinda means that we need to fix our code. This isn't the code which we need to fix, but this is the code which we need to fix. And to fix the code, we basically need to increase this from, yeah, to the address of 1A2084. Is it 84? It's 88 actually. Okay, and now let's do it again. Yeah, it's a little bit longer, but there are a lot of zeros. So the zeros are actually like, we maybe not care about them at all. Okay, let's take a look again. It's loading, perfect. Why is it? Yeah. Okay. But there are a lot of zeros here, so we do not care about that too much. Yeah, it's just like zero padded. So thankfully it's not that large. At the end there's probably nothing anyway. Let's just go to the end. Yeah, so we can actually cut it early. Where can we cut it? A lot of zeros. Yeah, okay. So there was some code here. And afterwards there's no code again. Oh, so yeah, we have this. Yeah, I'm afraid I know what's going on here. It's actually unpacking itself. Oh well. So next thing which I would recommend doing is actually checking what it does it write to memory. Because that's actually pretty interesting. It takes each of these addresses and it writes to memory, but it's almost always this 777 thing. Yeah, it's always this 777 thing. Which is weird. Wait, oh no, it's not. And then, let's try to analyze what we have. What I want to do now is, I guess I want to grab this piece of code and, yeah, I would like to decompile it, basically. How do I write a simple decompiler? I totally don't want to overwork myself to writing the compiler. I can probably generate proper C language. If I can generate proper C language, I can compile it with LLVM with optimization, and then I can read it in IDA and decompile it, right? And I'm pretty sure I can do that for most of it. I'm going to check one more thing. Unknown gadget. Okay, this is cool. These are basically, I'm pretty sure these are the addresses where the jumps are happening to. So, and again, we need to decrease it by 4. So, yeah, let's try to, no? So decrease it by 4, increase it by 4, increase it, so C. That's not working. I'm pretty sure it's somewhere in these constants. Why is it not here? Alright, maybe I'm calculating something wrong. Weird. Maybe this gadget is not used. Yeah, here it is used. So, yeah. What we know already. It's puts something in memory, right? Some stuff in memory. Then it has this large switch case, which goes somewhere else. And this somewhere else has some unknown gadgets which we need to analyze. And there's like this gadget, this gadget, this gadget, these gadgets, and so on. So what we should do now is we should basically we should first figure out which D word is the last 0, like the last non-zero value, and cut it. So let's do it like this. Last non-zero is 0. Okay, now I'm going to already cut it by 4 bytes to get rid of the magic, which is at the end, which the magic is here. Okay. Now, if D is not equal to 0, last non-zero is equal to I. Print hex I. Okay. Tail. And this is absolutely not working. If D is not 0, it's 0 here. Why does it say that it's this? What did I do? D of I. Yeah, exactly. Why did it do this? Oh wait, no wait. Last non-zero is fine. What's wrong with this? If D is not 0, and that's the word of I. Oh, I'm sorry. Maybe I'm tired or something. That's so stupid. Okay, and this is the last instruction, which has okay, yeah. So here, let's go to this address. This is the BE130. BE130, and let's regenerate the file. Okay, and it's cut now. Here we can remove writing this, and this is fine. Perfect. Now, okay, now we need to disassemble the gadgets. And furthermore, if it's an unknown gadget, we need to add it to a set of unknown gadgets. And you know what? We were using this here, but actually what I'm going to do is I'm going to do if desk is, I'm sorry, this is nasty. Don't do it. This is like not a proper way to flag it, but I'm still going to do it. Okay, then list all the gadgets which we are not handling. So let's do a tail of it. There are a couple of which we are not handling, so we do need to analyze them as well. So let's just go back to business, basically. The business of reverse engineering. Okay, so here. Is the address correct? 30, it is correct. It's move ZX EAX is basically like load into EAX, but we are actually loading a byte from EAX. So this is just loading a byte. Then it's popping EDX. We actually know the drill. So EBX equals this, and we are going to use this as well. Now, next one, G. Here, address matches. You know what? I'm going to actually move it a little lower. And this is just a load, no, a store. So this is a store. Into EAX, we store the value of ECX. Okay. Next one. Here, third one. Is the address correct? F6 is not correct. I'm going to undefine it, and I'm going to pop PSP. That's a jump. That's a jump. Into the whatever address I give it. And we can use this opcode pop thing. If you pop something to ESP, and ESP in return-oriented programming is your instruction pointer. This is the instruction pointer when this is a jump. Next one. Okay, this is also a load. Load into ECX, whatever is at the address pointed to by ECX. 2 times EC, correct? Is that correct? 2D, yeah, that's correct. Here, is the address correct? It is correct. EBX sysinfo. This is just an exit. That's weird. Am I really jumping here? Why would I be jumping here? Why would I be like doing this DL? What sysinfo? Oh, it's okay. Yeah, I might be jumping here, I guess. So no, this is a syscall. I don't know, like, looks weird. Is it exit? We're going to look at this only if we care. Here oh, this is actually like, oh my, how to write it? It's EDX and EAX are actually equal to EAX times ECX, right? Please correct me if I'm wrong, actually. And next address. Aligned to what? There's no such instruction as align to. 39 39 CC. Come on, undefine this. Yeah, this is a CC. This is an int3. This is a break. Like a stop, like a fault. Let's write like a breakpoint. So let's write it as int3. Maybe this is for debugging. This looks like somebody just added this by hand, by the way. Maybe some opcodes were missing. Freebie is sorry, XOR EAX with ECX. We have XOR. That's cool. EAX XOR with ECX. That's fine. And then we have E3. Surprise, surprise. Which is just a line below, and this is EAL is or ECX. Okay, perfect. Now we have all the missing stuff. We can regenerate the file, our disassembled file, and we can again look at what's going on here. Okay, so there's some code here now. Okay. We have it disassembled nicely. This is storing stuff in memory. Then we load stuff and yeah, I guess from here you can already try to analyze this challenge. Now we have storing in memory, we have this large switch case with jumping into different points and comparing ECI. Where's ECI coming from? ECI is coming from EAX. EAX is coming from EAX, and EAX is coming from EAX plus 4, where EAX is this. Okay, this is like a lot. Here we are obviously zeros because it's not runtime. We can debug this, by the way, quite easily, thankfully, using GDB. So yeah, I guess like setting breakpoints is a little more tricky, but it's doable. Perfect. And then it jumps into different things. Depending on the ECI. And afterwards, what's happening afterwards? Okay, let's go to the end of here. When the stack pivot, if it doesn't jump, then it actually goes here and it starts putting stuff in memory. Oh, wait. This is ASCII. This is ASCII. So if this is ASCII, what we want to do is we want to decode it. And since we want to decode it, I'm going to copy it. Yeah, let's copy this and let's like do another file like help UI. That's not UI, that's PT. Okay, I'm going to remove everything which isn't ECX. Yeah, I was thinking if I can do it with a regular expression, but I'm too... How do we address, by the way, differs? It's 9, C, it's increased always by 4. Okay, so this is just continuous store. Okay, now let's do this, and now we have a table of dwords, so that's k equals a table of dwords, where I forgot obviously the commas. Okay, so now for let's create an output. Okay, and let's like put these together. So we basically want to pack the we want to pack k as we want to pack as an integer k for x in k, and then we want to join it and we want to just print it, whatever. Print. Okay, Python help. Okay, fatal error, VM failed to recognize opc, which means probably we truncated this a little bit. Yeah, there's also like a 64 here and 65 there and 2e. So we have a couple of more. So that would be, what's the order? I don't know. Let's try it like 64, 65 and 2e, and like let's place 2e twice. Okay, yeah, fatal error, VM failed to recognize opcode. VM, which means this is a virtual machine implemented in return-oriented programming. So this is a stacked VM. We have 2 layers of VM, and the switch case which we are looking at, that's actually another VM being like selecting which opcode of the other VM to execute. So we basically have another VM to execute. By the way, so you're writing on the chat that I could just use bin ASCII and hexify. Yes and no. This is little endian. If this if it wouldn't be little endian, I would do as you say, but this is little endian, so I needed to use this thing because it changes the little endian thanks to this character here. So yeah, so we basically have a nested VM, like a VM inside a virtual machine, which means that we now have to do something completely different, which means we have to analyze the new virtual machine. Thankfully, to analyze a new virtual machine, what we know is we know that this is the switch case, which means each of these EDX here, each of these is actually an opcode. And no, sorry, this is where the implementation of the opcode, and this is the opcode. Because ECX is compared to what is in ESI, and yeah, and 077, these are all the opcodes, all in, not here, but above. In ECX, the opcode, then we have whatever. Now, if we scroll up, actually, and this is the storage at the beginning, where I said some memory is being initialized. Notice, what is the memory initialized with? The memory is initialized with opcode. So this is basically where the program of the second layer virtual machine is being put in the memory for later the virtual machine to run through that thing. So what we basically need to do is we need to write a second disassembler for this. But before we get there, we should store this. We should store this second layer bytecode somewhere in a file so we can analyze it. Okay, and to do that, what we need to do is basically, I'm going to cheat a little. And to cheat a little, what I need to do is I need to find the end of this. And the end of this is, I know. Yeah. Alright, it's here. So here's the last store, and the address of the last store is like the I is this one. So in my disassembler, I'm going to collect all these D words. So layer 2 bytecode is this. And then I'm going to collect them. So if we get here, if I is less than this value, this is hexadecimal value, then to layer 2 bytecode we want to and if we are setting, this is what we're storing, ECX, so ECX, I'm sorry, this is going to be nasty, don't look. If ECX equals in used index, then we are going to append, I hope you're still not looking, D words of I minus 1. Okay, this way at the end we should have everything. Let's just go for L2 in layer 2 and print hex L2. Yeah. Okay, so this absolutely failed. Should it be -2? Yes, or did I do something wrong? ECX is set to, yeah, ECX is being set to this, so that's ECX. Y is whatever was returned. Where are my beautiful, did I make a typo? No, it's ECX. Not EDX, right? ECX minus, wait, I is not increased, it's I, okay, yeah, sorry, that's a stupid mistake I've made. Alright, now it's perfect. So we have this virtual machine, which does something, and we have no idea what does it do, but yeah, we have it, which is better than not having it. So this is the bytecode, right? And how do I want to just store it somewhere. Alright, I need to do this, perfect. Now at the bottom I have this. Thankfully this is super short. There isn't too much stuff here. So layer 2 txt. Here we go. This is by the way reverse engineering 500, so this isn't your basic reverse engineering task. It was supposed to be a little more complicated. And what we have to do basically is we have to start figuring out the bytecode of the second layer virtual machine. So first we need to check in our bytecode, in our ifs. So let's do this and let's scroll down to the switch case. Where does the switch case jump based on sevens? The sevens are nowhere to be found. Here. Okay, and it jumps, this is this code, so it jumps here. Let's go to this address. Okay. So it jumps, I think, to this address. Yeah, here it jumps somewhere else, so this is basically here. And it does stuff. Quite a lot of stuff. And then it jumps back. Where does it jump to? I can tell you where it jumps. It jumps to either some iteration thing or the beginning of... Yeah, it jumps to the beginning of that if loop. So this is the if loop, which we are like the switch case for the second layer virtual machine. So yeah, this is like a totally a virtual machine. Like it's a switch case in a loop. That's how we recognize virtual machines. Okay, so let's go to here. Perfect. And this is what's going on. This is quite... Where was that jump? Yeah, anyway, here is the code. So it grabs something from EAX. I think based on the code which I saw before, this is a sequence which basically gets you the pointer in the address of the layer 2. This is the instruction pointer of layer 2. So it is going to be either pointing here or pointing here. Then it puts this in EDX. Why would it put this in EDX? What kind of address is this? It's some memory, some region in memory. Okay. Then it puts EAX in that region of memory. Then it does whatever is going on here, like puts the same address again. And it loads something else, and it decreases it through EAX. Then it okay, I'm losing track, which when it stores, so it stores memory under this EDX, under this address, then it stores memory under this address, then it again decrements something. What does it do? I mean, I see what it does, I do not understand why does it do it. It basically loads some stuff and then it stores it in EAX. EAX being this. Oh, then it's another store. So it load store, load store. That's pretty weird. I'm not really sure what it does. I'm looking at the hour. I think we are going to have a part 2 of this next week, because we are like halfway through the analysis. So I'm going to probably wrap it up in a couple of minutes, and then we're going to do a part 2 with finishing this KrzaQ next week. This is interesting because there is an XOR here. So what is being XORed with what? That's one question. Can we do something like, let's look here. Can we do XORs of things together to make it, to just break it without thinking too much about it. This is quite funny. This is like 4 bytes, 3 bytes, 4 bytes, 3 bytes, 4 bytes, 3 bytes. This pattern is interesting. Okay. I don't know why it does it. Then there is this, then this. Yeah, we're going to have to analyze it. There is no going around it. I was thinking if there's like something which I can just XOR together, because there is XOR obviously here. Can I XOR some stuff together? Does it give me anything? It's not clear. So I guess I'm going to wrap it up for today. What I'm playing is, I'm playing with an idea of actually, yeah, this is an easy opcode, for example. I guess I can break the opcodes by the jump. I think I've like started with the most complicated of the opcodes for some reason. Like this is like really obvious what this opcode does, right? It just puts this value here and that's it. Which is weird, why would it put it there? But whatever. Whatever. Anyway, I'm playing a little with the idea of, as I mentioned, basically making these strings be normal x86 assembly, for example, or being normal C code. And then compiling it, getting x86 assembly and disassembling it and decompiling it with IDA. Because that might make it a little bit more readable for me. Because like every jump you can switch to a goto, right? Every this you can switch to basically like unsigned int edx equals ecx, and you can just define edx and ecx as unsigned int 32-bit. Then if we go here, right, like every if 0, you can basically every this switch it to, well, basically this was already here, but actually before doing that you can do like zf equals to is eax equal to ecx, and then this line, and this is also starting to be proper C. And you put everything like this, then you put it in some compiler, you compile it and you decompile it and you see what you get. But I know what I'm going to get here, and this code isn't super complicated, so I'm wondering if it's worth the effort. Oh well, it doesn't matter that much. We are going to get back to this next week and figure it out. For now, it seems that this VM is pretty simple. We just have to analyze the second layer of opcodes, write a disassembler for this stuff, which is pretty much what we already started doing for the first part. Commonly, you might also want to mark all the jumps, like where the things are going, or you might actually want to generate a graph out of it, as in, you know, actual like IDA shows you a graph, right? But I do not see a reason to do that, because this code, there isn't a lot of code, and the code seems to be split into the storing a lot of data stuff, the switch case, and the implementation of opcodes. There isn't that much code, so I do not really feel the need to do any fancy thing, to add any fancy thing to this disassembler, which I have done multiple times in the past. So let's finish here, and let's continue next week on the second part of it. And for now, let's go with any questions if we have any. Okay, so okay, the questions are still not showing. That's pretty weird. I'm going to need to check out later what's going on. A question from Elvax. Do you know, can you say something about bit slicing in crypto? Bit slicing is a technique where computation is reduced to elementary operations like gates. It's called bit slicing. Okay, I didn't know it's called bit slicing. I'm reading basically it on Wikipedia. For constructing a processor. I'm not sure how bit slicing is related to crypto. Anyway, I've implemented it once or twice for SAT solvers, basically, where the idea is that we took x86 code and then written manual translators basically from x86 code into gates, basically, or actually into SAT expressions, which are basically AND gates connected with OR gates. And having that, we put it into SAT solver to solve it, because SAT solver was so much faster than an SMT solver. So I've done it once. It was for crypto purposes. It was actually for recovering, having a decryption algorithm, and the decryption key, I needed an encryption algorithm or something. So yeah. So I've done it once, but I cannot tell you too much about it because I've done it again once or twice. I've done it once on a CTF and then maybe like once more or twice more. So yeah, I cannot say too much about it apart from that it exists. And I'm not really sure how really useful it's in crypto, so we would probably have to ask a cryptographer, like a real one. I do not pretend to even know crypto decently enough to turn this above 300 points on CTFs. Why are you splitting the stack into D words? I think that drop gadgets instructions could change stack pointers by 1 and shift the alignment of the stack, couldn't it? It could. That's a really good question at the line, but it's so super rare to see the stack being misaligned. I'm not worried about it. If we would end up with such a situation, then I would handle it, but it's super rare to see the stack being misaligned for any purposes. Furthermore, some APIs stop working when you have the stack misaligned. So yeah, I'm not worried about it. But it's a really good point. But that might happen. Somebody might on purpose misalign the stack, but that is super rare, and gadgets don't do it. Gadgets always pop 4 bytes, basically. So, like a multiplication of 4 bytes, right? A product of 4 bytes. Database Advisor, a question for the end. Could you show how to reverse engineer closed source drivers? I would like to port some drivers, but I don't exactly know how to do that. That's always a little risky, I guess, because this stuff is usually protected by copyright laws, and I'm not sure I can do that on a live stream. It's like, copyright stuff in reverse engineering is pretty complicated, so I'm probably, unless I'm going to first write a driver and then show how to reverse engineer it, I cannot show how to do it. But then, that being said, I can reverse engineer my own driver, and that's perfectly fine. So I will get back to you as soon as I write some decent hardware driver for myself, but it's like normal reverse engineering. There's no magic there. Like, if you know how drivers work, then it's normal reverse engineering. It doesn't differ that much. You have to have some knowledge about the electronics of the given thing, and ideally, if you have the hardware, right, try to look up the data sheets for the hardware, because the data sheet plus the assembly code for the driver, like even the data sheet should tell you a lot about the hardware, and way more than the driver can actually. So the data sheet would be the more important thing here. Like, just look at the chipsets which are there, and maybe you'll find something, like the chips, right? But it's an interesting idea. Maybe we'll get to that. Okay, Dohan gave me a link, and the link is actually pretty cool. So let's look at the cool link. Where is my browser? Yeah, I think I'm asking this question a lot, like, where is my console, where is my browser? Maybe I should stop. Randomly XORing data, the definite CTF guide. Wow, I didn't see it. That's funny. I'm going to save it somewhere. I'm just going to keep it open then. I'm going to put it here. Yeah, perfect. I guess I can show you my favorite book cover. That was yeah, this one. Yeah, I always found it super funny. Like, especially like this, like the author with his therapist, so that's oh well. Let's look if there are any other questions. Who cares? How likely is that Google will be broken up by antitrust litigations? It would be great if that happened. No comment. What else can I say? You know, I'm not a representative of the company, so no comment. Okay, perfect. I think that's going to be it for today. Now, oh, I do see there's a donation from Pavel. Nice Matryoshka, waiting for Cyberpunk 2077. Thank you, Pavel, for the donation. I'm not sure why the banner didn't appear. Maybe it will appear in a couple of seconds. Oh, it's here. Perfect. Yes, I am waiting for Cyberpunk 2077. It looks amazing. I was a huge fan of the previous games of CD Projekt, like Witcher, and yeah, I'm really looking forward to Cyberpunk. I really like Cyberpunk games. Like I played a lot of Deus Ex, both the original and like the Mankind Divided, Human Revolution, and so on. So I even enjoyed the Deus Ex 2, which was pretty fun, and a couple of other games as well. So I am waiting for it. It should be fun. It looks amazing. So yeah, perfect. Thank you for today, folks. I'm going to see you next week. And remember that at the end of next week, there is Google CTF. So put that in your calendar because it's going to be fun and a lot of fun. That's it. I'm going to leave you with some music. Again, thank you for KrzaQ for being here as my moderator. And I think Disconnected jumped in later on as the moderator as well. So thank you to Disconnected. And I'll be seeing you next week. I'm going to leave you with some music, folks. Have a great day. Have a great evening, whichever time zone you're in. Bye.